Hi class. Today we're going to talk about eigenvalues and eigenvectors. This is section 5.1 and 5.2 in your textbook. However, it doesn't make sense to talk about one without the other. So this is just a merged lecture. So we're going to talk about both of them at once. Okay. So if we move on. Let's first talk about this definition, right? So I know there's a lot of symbology here, which is fine because we're going to talk through it, which is the purpose of having a video and not just reading a textbook, right? So this is our definition for eigenvalues and eigenvectors. Say that we have a matrix A that's n by n with real values, okay, and a vector U that is a element of Rn, so it has n elements, and all of its elements have real values. So again, this is n by n, and then this is a vector. You can think of it as a column vector with n elements. So n by n, and then U is an n size vector. Okay. Now our vector U, it cannot be the zero vector. It cannot just be a bunch of zeros. Okay, so it's a non-zero vector. We call U an eigenvector of our matrix A if this backwards E, we've talked about this before, okay, maybe once or twice, it means that there exists, okay? So U is called an eigenvector of our matrix A if there exists a value which we call lambda that is a real value, okay? So this lambda here is a real value such that if I multiply A and U together, so that n by n matrix times that n size vector, okay, then we get out the same thing as if I were to multiply U times this constant value. So remember, elements of R are constants. Normally we call these A, B, M, N. Here it's a lambda. It has a very specific use, so we are calling it the lambda notation. Okay, so basically what this is saying is that if I multiply my vector times A, I just get out a constant multiple of my vector, right? So again, think about this as a matrix transformation. Remember, the transformation where A is a transformation matrix is A times X equals B, right? So this is basically saying if I put U under the transformation A, I'm just going to get out a constant multiple of U, right? So if you guys watched that 3 blue, 1 brown video on eigenvalues and eigenvectors, they talk about that quite a bit, about how this vector just gets basically stretched in some form under the transformation A, right? So that's a good way to visualize it, right? So go back and watch that video if you haven't already. Of course, this is a lecture video, so this is all the math that's behind it, right? So if this is true, then lambda is called an eigenvalue, right? So let's go through that one more time. A is an n by n matrix. U is an n size vector. That's not the zero vector. Then if our matrix times our vector just gives us out a constant multiple of that vector, then that value, that constant multiple value, is an eigenvalue, and the vector U is called an eigenvector, because this doesn't work for every vector. It's just certain sets of vectors that this transformation does this to, right? So U is our eigenvector, lambda is our eigenvalue, right? So that's the definition, that's the explanation. Hopefully that made sense to you guys. If not, it's on video so you can rewind it and listen again, okay? So let's start with an example. So let's consider a matrix A, right? That's our n by n matrix, and a vector U. Right, so in this case, we're using the vector negative 1, 1. So what's going to end up happening is that we're going to find this vector. So right now, for this first example, we are going to assume we have this already, and we're just showing that this property holds. Okay, but the purpose for this section is to start with a matrix, find this value lambda, and after we find lambda, we're going to find this eigenvector that is associated with this eigenvalue. Okay, so we're kind of like jumping the gun here, but that's because we want to show some examples, right? So we have this matrix A. We're assuming that this is a random vector. Okay. If I multiply these together, then I'm going to get 1, negative 1, which if you notice is the same thing as u if I were to change the signs on both entries. Okay, so a times u is just negative u. That means that my lambda, right, is this constant, which is negative 1. Okay, and that also means that u is an eigenvector. Now, if I had chosen a different vector, it probably would not have worked out this way. Okay, so again, these things are pretty unique to the system that you're in, right? So u equals negative 1, 1 is an eigenvector of this matrix A, and lambda equals negative 1 is an eigenvalue of A. And these things are associated with each other. This eigenvalue gives us this eigenvector. Okay, that's how that works. They're paired together. Okay. So again, right, just note that the transformation of A on U maps U to a multiple of itself. In this case, negative 1 of itself. So again, right, so as we were saying, what we're going to try to do here is, given a matrix, is find this lambda and find this u, right, instead of us kind of working backwards from our end result. So how do we do that? How do we find eigenvalues and how do we find eigenvectors? Well, again, eigenvalues are first and then come eigenvectors. So let's go through a derivation here. We know that lambda is an eigenvalue if this property is true. That is, a times some vector is just a constant multiple of that vector. That's what we just worked out, right? So if I move some things around, then the 0 vector is equal to lambda minus a times x. So I basically just subtracted this on both sides. Okay, I can factor out this vector x. So we saw that there's certain properties that we are allowed to do when it comes to matrices. Vectors are considered a form of a matrix, right? We're just talking about vector spaces and the properties that hold and don't hold. So we can undo the distribution property, because we could have distributed this on the right side of everything. So we can pull it out as a right side sort of factoring process. Okay, we cannot put this on the right because this is on the right side of each thing. It is not on the left side. X is not on the left side of each of these. So I could not factor this to the left. It would have to be to the right because everything else is on the right. Okay. So now if I take the determinant of both sides, because this is a matrix and this is a matrix, without this x value, without this x vector, lambda I minus a is a matrix. So again, lambda I is really just the identity matrix multiplied times the scalar of lambda, right? So this is I with lambdas everywhere we would normally have ones. Okay, so for this matrix, if I take this determinant, it'll be the same as if I take the determinant of the 0 vector or a 0 matrix, okay, which will be equal to 0. So we're going to use this property to help us find eigenvalues. Okay? So therefore, the determinant of lambda times the identity minus our matrix A equals 0 if lambda is an eigenvalue, because again, these things have to be equal, right? The only way for that to be equal, basically the determinant of a 0 matrix, is if this works, right? And again, this 0 matrix is not equal to this. This lambda I minus a is not a 0 matrix, but if I were to multiply this matrix times the vector I have, x, I will get out the 0 vector. Okay. So this value, the determinant of lambda I, lambda times the identity minus a, we call p of lambda, right? The determinant gets us out a value. In this case, we're going to have an equation. So we call this equation the characteristic polynomial. Okay, and the roots of this polynomial that we find, those are going to be our eigenvalues. Okay, so let's do an example. So let's consider the matrix A, which is 2, 0, 2, 5, negative 3, 14, 1, negative 1, 4. Right. So again, I'm bringing these as column vectors Because if you haven't noticed, that's kind of what we do. Like sometimes we think of them as row vectors. Most of the time we're looking at these in terms of their columns, talking about bases and column space and things like that, right? So let's just look at this matrix, right? If we start to build on some of the things that we have up here, for instance, this part, right? I need to take the determinant of this thing, this lambda I minus a. So maybe I need to kind of find that first. So we'll go through the process for this first example. And for the examples after this, we'll see that it's actually very, very easy to calculate this thing right off the bat without even kind of going through the process. Okay. So my lambda I minus a is going to be the identity matrix full of lambdas where i's are supposed to be, because I'm multiplying the identity times lambda. Now remember, it needs to match in size with a. So if a is 3 by 3, my identity is 3 by 3. Okay. I had a student one time say I didn't know what this I was because I didn't see the little subscript n here. We don't normally write the subscript n. I don't normally have to say I3 or I5 or what have you. Your identity is always going to be a square matrix. If we have it in this kind of notation, we just need to match up with the dimensions of our a value, a vector. Okay, so if my a is a 2 by 2, I'll just be using the lambda 0, 0, lambda. It'll be a 2 by 2 version of this, right? So your identity is always just matching in size to whatever dimensions it is that you're working in. Okay, so if we calculate this, we take our lambda scalar identity and subtract our a matrix. Basically, everything turns negative, and we're going to get lambda minus the entries in our diagonal. Okay, so this is actually very easy to calculate off the fly. Lambda minus 2, lambda plus 3, lambda minus 4. So all these values get negated and a lambda in front, and then all these values get negated also, right? So 5 is negative 5, 1 is negative 1, 1 is negative 1 is 1, 0 stays the same, everything else just goes negative, and we're subtracting the main diagonal from lambdas, right? So this is actually very easy to just write off the bat. Okay. Now we're going to need to find this determinant. Okay, so our notation for determinant is not the same as the notation for matrix. A notation for a matrix has square brackets. For a determinant, we have straight brackets, like an absolute value sign. Okay, so my characteristic polynomial, p of lambda, is the determinant of that matrix that we just found. So I need to find this determinant. So I just put it in the proper brackets so that my readers or watchers, you, know that we are going to take a determinant. Okay, so we have a few ways of taking determinants. Again, all of this stuff that you guys see, I had to kind of code from scratch. Like, it was not written in like Word or anything like that. So the first time you do this is going to be the regular cofactor expansion, because that's easy to code to print. Okay, for the next couple examples, at least for the 3 by 3s, I'm going to do that 3 by 3 expansion where we repeat the columns, the first 2 columns at the end, and then we just do that 3 by 3 diagonal multiplication stuff. Okay, so when we get to those examples, you'll see that. But for right now, we'll just go through the cofactor expansion. Whatever method you have for finding determinants, go ahead and use. But these are going to give us equations out, so you kind of do have to do them by hand. So again, whichever method you like. If you notice here, I have a 0 here. So remember, cofactor expansion, I can go down any of these columns or any of these rows, right? Now, if I go this column, I have one cofactor I'll find that has a lambda in it. This one is going to disappear, so that's nice. And then I'll have one with the negative 2. So it'll be way easier to go through this. I guess this would have been kind of easy to choose also. 0 for the first one, and then a lambda, and then just a 1. It doesn't matter which row or column we go down, but we try to choose the easiest one. I chose this one. In hindsight, maybe this one would have been better. The second row, the 0 and the 1 in it. Oh well, okay. So our cofactor expansion down column 1 is lambda minus 2. Remember, this row goes away, this column goes away, and this row goes away. So we're left with these 4 entries as the sub matrix we got to find the determinant for. So I have lambda plus 3, 1, minus 14, lambda minus 4. Plus, minus, plus a negative is just minus, right? So then this row, this column goes away, and this is the sub matrix I have to find the determinant for. Negative 5, negative 1, lambda plus 3, and 1. Okay, so that's where this cofactor expansion comes from. So then I'll find the determinants of this and this. Remember, straight line means determinants. So this next line will be lambda minus 2. Remember, for 2 by 2s, you multiply this, subtract the product of these two, right? So this next line will be lambda minus 2 times this product minus this product minus 2 times this product times that product. Okay, and there you go. Lambda minus 2. Square brackets to differentiate between the sets of parentheses, right? So lambda minus 2 times lambda plus 3, lambda minus 4, minus negative 14, so plus 14, minus 2 times, right, big parentheses, negative 5, and then minus a negative lambda plus 3, so just a plus lambda plus 3. So from here, I'll multiply this out and combine my like terms before I distribute this lambda minus 2 in. So basically it's just algebra. I wrote all the steps so that we could see how this works. Again, this is a lecture video, so I'm trying to be as thorough as possible, especially since I'm not there in person for you guys, right? So here I have lambda minus 2. I'm going to simplify this portion of the parentheses, which I have, and then I simplified this portion. Okay, so I got a negative 6 plus 10. So that's 4, and then negative 2 lambda, and then this is just a regular polynomial, right? So you got plus 3 minus 4, so that's minus 1, and then you got the negative 12 for multiplying them, plus 14. Okay, this next line, I added this together, that gets me 2, and I distributed this across as well, right? Lambda times lambda squared, lambda times the negative lambda, lambda times the positive 2 that I would have here is the 2 lambda, negative 2 lambda squared, plus 2 lambda, and then this would be a positive 2, and my negative 2, which is where I got the negative 4, right? And then this negative 2 lambda plus 4. So then now all we have to do is combine like terms, so the lambda squares and the regular lambdas, and then as you can see here, this minus 4 and plus 4 will disappear, and I have this polynomial. Okay, so factoring is going to be extremely important in this portion of the course, okay, for as long as we deal with eigenvalues and eigenvectors, which is kind of a while. Actually it's kind of the rest of the semester. We're going to use these a lot for a lot of things, so I will post some more things for helping you guys practice factoring. Those of you who are also taking my DiffEq class, we went over that in class right before the break, so that's nice. A lot of those methods will come in handy, especially once we get to the cubics. We're gonna have quite a few cubics that will have to factor, and I know most of you guys are really only kind of familiar with factoring like quadratics and things like that, right? Or special forms of polynomials. So I'll make either a supplementary video or I'll post a video from YouTube, because I got to make videos for all of my other classes. So I'll post something to help you guys for factoring these larger polynomials. Okay. So we can factor out the GCF here, and now we have lambda times a quadratic. Again, you don't have to use quadratic formula for everything. This factors very nicely, and in general they will. There will be times when they don't, but we are not at that point yet. Everything here should factor pretty nicely. So the roots of this polynomial are my eigenvalues. That's why they're in terms of lambdas. So lambda 0, lambda 1, and lambda equals 2 are my eigenvalues, right? So the characteristic polynomial equaling zero implies that these are the zeros of the characteristic polynomial, which mean that they are the eigenvalues of my original matrix A that I have here. Okay. So to find the eigenvectors, now that we have the eigenvalues, we need to solve this equation that we had, right? Where I have lambda I minus A equals 0 for each eigenvalue lambda I that I just found. So basically what I'm going to do is I'm going to plug in 0 for this lambda and then calculate the resulting matrix, set that equal to 0, and solve it. Okay, so we're getting back into row echelon forms. You can use inverse matrices. You can use whatever you want. Although I'm going to suggest to you to use the reduced row echelon form. Again, you can calculate that on your calculator. That is going to be the most helpful way to find these, because what's going to happen is all of these things are going to be dependent systems, right? So when we solve them, they're not going to solve all the way. So using an inverse matrix here isn't going to help too much. We're going to want to actually solve these down into reduced row echelon form, right? So for lambda 1 equals 0, I'm going to get this matrix. If you notice, the only thing that changes is the diagonal, because this was lambda minus 2, lambda plus 3, lambda minus 4. All of these were negative, right? So I'm just plugging in the lambda values here into each of these parts. So for 0, it reduces to negative 2 plus 3, negative 4. When I get to 1, I'll put 1 here. So this would be negative 1. This would be 4. This would be minus 3. And the other values that are not along the diagonal stay the same. Okay. So if I put this down into reduced row echelon form, right, where I'm setting it equal to 0, I get this as my system out, right? So again, it's always a dependent system, so I'm always going to have a free variable. If I don't have a free variable, I messed up somewhere. Okay, there's an issue either in my calculating this diagonal value or in the row echelon forms that I use. If I'm using the calculator, then it's definitely in my prep work for this. Maybe I forgot that I need to negate all the values here, right? It could be, it's always something small, right? But if I don't have a free variable somewhere, I messed up, right? So here you can see that I have a pivot position here, pivot position here. There's no pivot position here, right? Also, you can see that this is an entire row of zeros, okay? So if I solve this out, okay, remember this is the equal sign, so I'm adding this to one side and I'm adding this to the other side. I basically have x2 is negative 1/3 x3, so this is the x3 variable, and x1 equals a positive x3. So if I take this and I turn it into a vector, right, we've done this quite a few times, then my x1 vector, this is my first eigenvector, is going to be 1/3, negative 1/3, and 1. So if I let x3 be 1, x3 is 1, these are my values. And again, any multiple of this vector works. If I wanted to, I could have put in 3 here, and then this would be negative 1 and just 1. I can multiply this entire thing out so that they're all constant whole integer values. And although that's going to look good, later on, if we develop that habit, it's not going to be very useful to us. Okay, in fact, we'll see some some nice things happen from keeping these original values. Okay, so again, if we change these into full integer values, so 3, negative 1, 1, that is an equivalent eigenvector, although that might help us to develop bad habits for some of the later things that we're going to be doing. Okay, so it's normally a good practice just to keep it in this form, right? x3 is 1, and then the values that you get. Okay, so that was for lambda equals 1. 0. So now we'll do lambda equals 1, and then we'll do lambda equals 2. We'll do the exact same process. So we're solving this thing 3 times. Again, this could be a pain in the butt to do by hand over and over. This one problem, if we just think about what we have here, right? Starting with this matrix, calculating that, calculating this determinant, solving this polynomial, looking at each of these eigenvalues, and then doing this process, putting it into row echelon form and coming out with a vector 3 times. That can be a very, very long process by hand. Okay, so you definitely want to use your calculator for these row echelon form portions of the problem. Okay. Note that we also don't need this 0 vector here. I really didn't need this. When you do row echelon form, remember, you're taking one row, you're multiplying it by something. This 0 will always be 0. I'm taking one row and I'm adding it to another row. This 0 is always going to be 0. These zeros are never going to change. They're nice because they help you remember that there's an equal sign right here, and you need to move stuff over to the other side of the equal sign. So that is important to help you remember that, but they're not necessary. Okay, and since they're not necessary, I'm not going to use them in the remainder of the calculations that we have here. I am going to remove the 0 vector on the end, you see. Okay, so let's go for lambda 2 equals 1. So again, lambda minus 2, lambda plus 3, lambda minus 4. Now lambda is 1. So here it was 0, now it's 1. So I'm going to get a different diagonal than I got before. Okay, the other values are still the same. I'm going to reduce this into row echelon form. Sorry, reduced row echelon form. So I want to reduce it as far as I can. Right, and I have a similar output, but it is not negative 1/3 and 1/3. It's the 1/4. So it's going to be the same thing. I imagine there's a 0 vector here. My x1 will be the opposite value of what I see. My x2 will be the opposite value of what I see. Okay, so this is what I'm going to have, and that gives me my x2 vector that's similar in form to this. Notice that they are linearly independent. I know they look the same, but these are not multiples of each other. Okay, there's no way for me to multiply this by anything to get this thing out. They are not constant multiples, and they should be linearly independent. All 3 eigenvectors in this case will be linearly independent from each other. You should not have a set of linearly dependent vectors. They should all be linearly independent from each other. Okay, so if I get one vector that's a constant multiple of another one, I have a problem, right? I messed up somewhere. So let's look at the third eigenvalue that we're going to use to find the third eigenvector. So this is lambda 3 equals 2. When I plug it into my lambda value in the diagonal, it will reduce down to this matrix. Okay, so again, lambda is now 2, so 2 minus 2, 2 plus 3, and 2 minus 4 is how I got these, right? So again, just to recap, that's coming from this matrix, right? This lambda I minus a. Okay, reduce this row down again also, and I have this as my result. Again, there's an imaginary 0 vector here on the other side of the equal sign, so I move everything over, basically change the signs. Okay, my free variable in all of these cases was x3. That's not always the case. Sometimes it'll be x2. Sometimes I have more than one free variable, right? But to write this solution down, I now have my 3 eigenvectors, okay, and they are all linearly independent of each other. And so those are my eigenvalues and their associated eigenvectors. Okay, there you go. And that's the process we're going to do for pretty much every problem in this chapter, although we are going to expand on this process quite a bit, but we are going to do this a lot. Okay, there's going to be a lot of eigenvalues and eigenvectors for really a large portion of this class. Okay, so the eigenvectors x1, x2, and x3 form a basis for the eigenspace associated to their respective eigenvalues. They do not form a basis together. They do form a basis together, but it's not called an eigenspace. The eigenspace is associated with each individual eigenvalue and its eigenvector. Okay, so for instance, this vector and all constant multiples of this vector forms a basis for the eigenspace formed by lambda equals 0. Okay, so this eigenvalue has an eigenspace that is formed by this eigenvector. Okay, so it's not all three together, it is them being paired together to form the eigenspace for that lambda value. So again, 1/3, negative 1/3, 1, that was the eigenvector we got for this eigenvalue. Eigenvalue, eigenvector. Those two together form an eigenspace, right? So this produces an eigenspace, and that eigenspace is spanned by this eigenvector. Okay, all constant multiples of this eigenvector produce a space, and that space is called the eigenspace, and that's associated to this eigenvector. All right, so again, one more time, these things are connected to each other. These two are connected to each other, and these two are connected to each other. So there's three different eigenspaces. Each eigenspace is determined by its eigenvalue, right? Okay, I hope that makes sense. You can replay that video and listen to that if you need to. Right? So, theorem. The eigenspace of lambda is a subspace of Rn. Okay? So let's think about this. The eigenspace is the null space of lambda I minus A. So remember, each lambda gives you a different matrix value, a different one of these matrices. So that's three different null spaces. So remember what a null space is? A null space is any combination of vectors that will just send you to the 0 vector, right? And that's basically what we did. We set these vectors, these matrices equal to 0, and we found the form of the vectors that get sent to 0. The things that get sent to 0 are all vectors that look like this, all constant multiples of vectors like this. So this is a basis for the null space of that particular lambda I minus A, right? So again, talking about null spaces, right? Another way of saying that is it's the set of vectors S such that S is equal to the kernel of lambda I minus A. So what is a kernel? We talked about it just a little bit. Your kernel is the null space of a transformation, right? So again, remember, we are thinking of this as a transformation. We're taking a matrix, I'm multiplying it times a vector, and I'm getting a result out. And since that result I'm getting out is 0, that means that all the vectors that work under this transformation are basically in the null space, right? And so for transformation, we don't call it null space, we call it the kernel, right? So in terms of matrices, it's a null space. In terms of transformations, it's the kernel. Kernel and null space, exact same thing. It's just, am I talking about a matrix equation or am I talking about a transformation? Here, it's pretty much the same thing. Remember, a matrix equation is the same as a transformation, right? So this is a matrix times a vector giving you another vector. So that's how I think about it in terms of matrices. In terms of transformations, this is my transformation matrix times some vector getting out a result of 0, which is its form in terms of the transformation, right? So transformations are kernels, matrix equations, null space, right? So the things that go to 0 is a null space, the things that go to 0 is the kernel, right? And these things are a basis for the eigenspace of lambda, right? So remember, your null space is a basis, okay? It's a set of vectors that span all the things that go to 0. Your kernel is the same thing. It's a set of vectors that span all the things that go to 0. all of those things in this case is a basis for your eigenspace of that particular value of lambda. Okay. So let's look at two more examples to explore the concept of what's called multiplicity within our systems here. Example, let A equal this matrix. Then our characteristic polynomial is us basically taking the negative of the things that are not on the diagonal. Okay, so 2, -3, 3, they change values. These also change values. And then we have lambda minus the entries on the diagonal, right? So let's go ahead and find this characteristic polynomial by doing our row method, our column method, I'm sorry. So I have the first 3 columns, and then I'm repeating the first 2 columns here. So apologies, but I couldn't figure out a way to overlay an arrow over my writing here, so we'll just do this by hand. So for the first part, remember the things going this way are pluses, and the ones going this way are minuses. So the first one is going to be lambda minus 1, lambda minus 7, lambda minus 2. That's going to be the first set of multiplications we have. And then we're going to multiply basically 9 times 6 and add that to 9 times 6 again. They're both negative, so we'll be subtracting those values. Then we will subtract this way, right? So 18 lambda minus 7, 18 lambda minus 1, 9 lambda minus 2, right? Take those signs into consideration. So you see we have this first part here from this diagonal plus, but it's a negative, negative plus plus, so that'll be a negative value. So we're going to minus 9 times 6. And then we're adding another negative 9 times 6, right? And then this is the other diagonal, 18 times lambda minus 7, and that's being subtracted. Negative 18 lambda minus 1, and that's being subtracted, so it's being added. And this is 9 lambda 2, and it's being subtracted, and it is negative, so that's a positive. Okay. It looks as though my lambda minus 2 maybe didn't make it here. Okay. But it did make it in this cut, right? So again, apologies. Sometimes when things are getting compiled in the process, not everything pops out. Okay. So I'll make sure to address that in the write-up that I post, as in the other video. Okay, so this should be a 9 times lambda minus 2, but here it did pop out in the calculation. Everything else, right, 18 times this stuff, add these together, and then here I started to combine my like terms, so negative 7 and negative 2 is negative 9. Multiply those, you get a positive 14, and there's lambda minus 1. So in the next line, I will multiply this out, and then I'll start to combine some like terms over here as I see fit. Okay. So in this next line, I multiply this lambda minus 1 across here. So I got the lambda cubed minus lambda squared, right? Lambda and 14 is 14 lambda. And then I just repeat this again, changing the signs. So negative lambda plus 9 minus 14. And then when I condense all this down, I get 9 lambda minus 18. So now I can combine my like terms again, right? You see 18 and minus 18 is a 9. Then the constants also kind of clear themselves out a little bit. So condense this down again, combining my lambda squares, my lambdas, and my constants. And I come down to this polynomial. And I want to find the roots of this polynomial, right? So again, this is a cubic. Factor by grouping isn't really going to work here. There's a few other methods. So again, I'll go over those with you guys in a separate video, or I'll post a link talking about how to factor higher order polynomials. But if we factor these down, you'll see that we get these as our vectors. Okay. So this lambda minus 4 appears twice. Lambda minus 2 appears once. So there's 3 terms here. Remember that? Lambda minus 4, lambda minus 4, lambda minus 2. So I only have 2 eigenvalues, 2 and 4. But I say 4 has algebraic multiplicity of 2 because it appears twice, right? So there's 2 4s here. I'm just only thinking of it as 1, but there's 2. We call this an algebraic multiplicity, okay, because it's a repeated root of our characteristic polynomials. So 4 has algebraic multiplicity of 2. Starting to find our eigenvectors, okay, 2 and 4. So I'm going to start with the single eigen value first before I go to the repeated root. So lambda 2, this is the matrix I get when I plug in 2 for my lambda value, right? So 2 minus 1 will be 1, 2 minus 7 will be minus 5, 2 minus 2 should be 0, right? And that's what I have here. For my diagonal, everything else is the same. Remember that it's lambda I minus a. So this is not just plugging it into my regular a value. These values are opposite values of this. So not 2, but negative 2. These are all positive also. Okay. It looks like I made a mistake in the coding here. I'll go back and fix that also on the script, that should be a 2. But the calculations were done correctly. Okay. So if I reduce this down, then I get this value out. Okay. Remember that there is a 0 vector on the other side here, so I can just move both of these values over. So they become the positive values times the free variable of x3, which will give me a eigenvector of x3 being 1. When x3 is 1, x2 is 3 halves. When x3 is 1, x1 is 3 halves. Okay, so that's what my eigenvector looks like. If I want to make these all whole numbers, I would use 2 here, and this would be 3 and 3. Okay. Again, if you want to check that this is correct, there's a way to check this also. We haven't talked about it, but we can plug this back into my equation. Okay, so what do I mean by that? Remember that lambda I minus a times this vector x equals 0. So I can plug this into that equation. So if I have 2i minus my original a, take that matrix and multiply it times this vector, I should get out the 0 vector. I'll go backwards real quick just to remind you of that equation. Okay, right? I can plug that into this equation and it should work. Plug in lambda, subtract a, this is your eigenvector, right? If we multiply this times our eigenvector, we'll get 0, right? If we go all the way back to the beginning, that's what we kind of did over here. We had an A matrix, I had a vector. I didn't know the eigenvalue, but now we can put all that together to check our values. Okay, so let's come back over here. This was the last example. Okay. All right, so here we are. All right, so now I come to my repeated root. Okay, my repeated root of 4. If I plug that in, I get this value. Again, it looks like I copied and pasted incorrectly in my code. This should be a 2, but again, when I did this work on my calculator, it was correct, right? So I just wrote it wrong. Again, I will fix that on my script, but I should get this value. Okay. So here I have a free variable at x is 2, right? In the second column. So x3 is 0, because remember all equals 0 here. And x1 equals x2 when I move this over the equal sign. So my x2 looks like this, 1, 1, 0. There is no third eigenvector. Okay. I have my 2 eigenvalues. This one has a multiplicity of 2, but it only gives me out 1 eigenvector. Okay, there's no x3 eigenvector here. It just does not exist. There's only 2 for this case. All right. So now let's take one more example. Let this be my matrix A. Okay. If I negate the values, it looks like this. Okay, and then I have lambda minus my diagonal. Right. So if it's negative, it turns positive. Everything else is negative. So I find the determinant of this, right? So this is my lambda I minus a. I find that determinant. Again, I'm just going to do the column method, right, where I repeat the columns twice. So do the diagonal arrows, the product method, and we should get out this equation. Okay. So I have these three here. If you notice, lambda minus I appears twice. So I have lambda minus 1 squared times lambda plus 5. I will add to that 3 times 3 times 3, 2 negatives, so it's all positives. And then I have that repeated again, so that's another 27. And then this is going to be my subtraction portion. So minus basically 9 times lambda plus 5, right? Minus this, so not negative and negative is positive, so I'm subtracting it, lambda plus 5. Same thing here, I'm going to subtract negative 9 lambda minus 1, so that turns into a positive. Same thing here, a negative 9 being subtracted gives me a positive 9. And again, I must have just copied and pasted from the previous example, so I have to fix that in both examples. This should be a lambda minus 1. But if you notice on this next line, that 9 did get distributed, right? So 9 lambda minus 1 plus 9 lambda minus 1 is 18 lambda minus 18, right? So basically 18 times lambda minus 1 and distribute that, okay? Then this is the part that coincides with this part, right? So these two parts go together. Again, it's incorrect as it's written, but it is computed correctly. Here it is the distribution of the 9. Here the two 7s are combined. And then here I figured it was easier to expand this before bringing in this plus 5. So on the next line, I will expand this and then combine these terms to start to simplify, right? So lambda plus 5 is being distributed into here, so I have lambda cubed plus 5 lambda squared, then times the second one. So negative 2 lambda squared minus 10 lambda, and then lambda plus 5. And all of this simplifies to 9 lambda minus 9. Okay. So again, you can see a negative 9 and a plus 18 is a positive 9, and then these things are a negative 9. Okay, because these are 9 away, and this is a minus 18. So you have plus 9 minus 18 is negative 9. Simplify that down. We have another cubic polynomial. Okay, this does not factor like if it was a lambda right here, right? There is a missing lambda term. It's multiplied by 0, so you have to, again, just know how to factor cubics, okay, in this case. So once we factor, we will get this out as our factors, which gives us our zeros. So again, I have another algebraic multiplicity. So negative 2 has algebraic multiplicity of 2 because it is a double root, right? If we were doing really large matrices and this was like lambda plus 2 cubed, it would have algebraic multiplicity of 3, right? So the multiplicity is just how many times does that root appear. So these are my roots, and then that is the multiplicity that shows up for that root, right? So now that I have the eigenvalues, again, we got to find the eigenvectors, okay? So the first eigenvector for lambda equals 1. That first root, the one that's not repeated, right? It's easier to do 1. I throw that in here. And when I do my reduced row echelon form, I get out this matrix. So I have x3 as a free variable. x2 is negative 1. x1 is positive 1. Remember, these are going to move to the other side of the equal sign. We're just not including the 0 vector here, but it's still technically there, right? So this is what I have. And again, it looks like my code is messing up. So I will, in the script, fix this for x3, okay? But that's going to give me this. If x3 is 1, this is negative 1, and this will be a positive 1. Okay, so remember, there should be an x3 here, not just a 3, right? So if I go to lambda 2, same thing. So lambda is negative 2 when I plug this in. I'll fix this also, right? It looks like there's a few errors going around that I didn't catch before we started this, but that's fine. So pretty sure there should be a negative 3. not it equals 3, right? So lambda minus 1, this is negative 2, that'll be a negative 3, right? So I must have just put an equal sign. Okay, when we simplify this down, this is the equation that we get. And if you notice, I didn't even have to use my calculator for that. These are all negatives, these are all positives, these are all negatives. So these two rows just go away, and I can divide this by negative 3. Very straightforward. I didn't even need a calculator for that, right? But that means I have two free variables. x2 and x3, those both move over. So x1 is negative x2 minus x3, right? So if I write that out, my solution to x2 looks like this. Right? When x2 is 1, I get negative 1 out for x1. When x3 is 1, I get out negative 1 for x1 because that goes away, right? So this actually gives us out two vectors, which means that this repeated root, since it has two vectors, it gives me basically x2 and x3 vectors, right? So these are not the vectors, these are the components, right? But it gives me vector x2 and vector x3, and we say that this eigenvalue has geometric multiplicity of 2, right? So I get two eigenvectors, and since it gives me two eigenvectors, the geometric multiplicity is 2, right? So the basis for its eigenspace has a dimension of 2, meaning that the null space is generated by a basis with two vectors, right? So this eigenspace is generated by two vectors, has dimension 2. There's a geometric multiplicity of 2, and that gives me my third one. So this is algebraic multiplicity of 2 and geometric multiplicity of 2. The last example had a algebraic multiplicity of 2, but a geometric multiplicity of 1 because it only produced one vector. Okay, so we're going to use that to talk about our next theorem, right? So again, the eigenspace of lambda equals negative 2 is the span of those two vectors that we got here, right? That x2 and x3 vector. Okay, so from the previous two examples, we can form our next theorem. All right. So for the first example, just to recap, we had an eigenvector that had algebraic multiplicity of 2 and a geometric multiplicity of 1, right? It appeared as a solution to the characteristic polynomial twice. It was a double root, but it only made one eigenvector, okay? This last example had an eigenvalue that had algebraic multiplicity of 2 and geometric multiplicity of 2, right? So it appeared as a solution to the characteristic polynomial twice. It was a double root, and it also produced two eigenvectors. So our theorem is that the algebraic multiplicity of lambda is always larger than or equal to the geometric multiplicity of lambda. So what does that mean? It means it can appear as a root to the characteristic polynomial equal to or more than the number of vectors it's going to produce, eigenvectors it'll produce, right? So the eigenvalue can show up equal to or more than the number of eigenvectors that it can produce. Okay, so I can have a multiplicity of 3, but it only produces one eigenvector. It'll never produce more eigenvectors than it shows up as a root. So moving on for that, let's talk about one last theorem. Okay, if k is a positive integer, right? So not a real number, but a positive integer, 1, 2, 3, 4, 5, etc. And lambda is an eigenvalue for some matrix A, and x is a corresponding eigenvector. So remember, the eigenvalue and the eigenvector go together. Then the kth power of my eigenvalue is going to also be an eigenvalue for my matrix A raised to the kth power. And that eigenvector is still going to be an eigenvector of that matrix A to the k, right? So there's some inherent properties that hold true for eigenvalues, and eigenvectors, and for the matrix that is associated to. All right, so let's do this as an example, and then we're going to end our lecture for this evening. So let's consider 2 by 2. 2 by 2s are way easier to work with when talking about eigenvalues and eigenvectors. So you will see a lot more of these than you will the 3 by 3s on your homework and in practice. But let's say we have A is this 2 by 2 matrix. Okay, our characteristic polynomial is going to be the determinant of this. So remember, the determinant for 2 by 2 is really easy. It is this product minus this product. Okay, very similar to the 3 by 3, but it's just one diagonal minus one diagonal. So lambda 5, lambda minus 2 minus this positive 4 that I get out. Okay, if we work that down, you get this polynomial, which is very easy to factor. Okay, which gives us this result, which gives me the eigenvalues of 1 and negative 6. Basically, you know, whatever makes this polynomial 0. So if I use eigenvalue of 1 and I throw that into here, I get 1 minus 5, 1 minus 2. So I get this. If you notice, they're just multiples of the other, right? So remember, you'll always get a dependent system. So 2 by 2s is really easy because you'll just have one row as a multiple of the other. Okay, so we get 1, 1, or x1 is negative x2, and then we can make our eigenvector from there. Let x2 be 1, then x1 will be negative 1. Okay, so that's my first eigenvector. We'll do the same thing with the next eigenvalue, lambda equals 6. So when I plug this in for lambda, I get the same thing. Again, one row is a multiple of the other row, right? This is just the negative value of this row. So that'll give me 1, negative 4, because this one will go away. And this goes on the other side. We're going to get x1 equals 4x2. So when x1 is 1, x1 is 4. So I should get 4 and 1 as my eigenvector. So those are my eigenvectors. So referring back to this theorem that we were just talking about, okay, we're going to raise it to a power and then raise our matrix to power, and we can see that it's going to be the same thing. Okay, let's see. So if I raise 6 to the 4th power, I get this value, and that's going to be an eigenvalue for a to the 4th. And it's still going to produce the eigenvector for 1. You can do this on your own to verify. Find a to the 4th power if you want to, and check that this property holds with this eigen value and this vector when you do the lambda I minus a times x thing. Just check to see if it goes to 0 or not. And then the same thing here. If I take the second eigenvalue, and I raise it to the 4th power, that will also be an eigenvalue for my A matrix to the 4th power, and is going to have the exact same eigenvector. Okay, and so that is our discussion of eigenvalues and eigenvectors. I hope this was helpful. I'll make a discussion board so you guys can have ask any questions that you have regarding this topic. Thank you.